Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our homework for day 1 of lesson 8.2.1. We're going to start with just some basic exponent type of expressions where we see the repeated multiplication, and we are going to rewrite them as an exponent kind of multiplication problem, or simplify it using exponent expressions. So all it takes is you take a look at this. You got how many 4s are being multiplied together? 2 of them, so that would be 4 to the second. How many 5s are being multiplied together? That would be 5 to the third. And we're not going to simplify this any further because we're not going to call that 20 to the fifth or anything like that, because that's not at all what this is equal to. It's not 5 20s being multiplied together. It's 4s and 3 5s. So I guess if you wanted to simplify it further, 4 times 4 is, stop it. 4 squared is 16, and 5 to the third power would be 125. And so we could do that if we wanted to, but there's no need to. We're just rewriting it so we can write this with powers. So let's just keep it as it is. Here you got 1, 2, 3, 4, 5, so 3 to the fifth power, y squared. And here, if we use commutative property, we would probably take away the parentheses because there's no reason to have them there. All we're doing is multiplying everything. So there's no reason to give priority for any of the multiplication parts. So you could write it as 6x to the fourth power, right? Because you literally have 4 6x's being multiplied together. Or you could remove the parentheses and rewrite it as 6 to the fourth and x to the fourth, which, by the way, when we learn next week about exponent rules, you're going to learn this particular problem right there is called the power of a product. Product being that these are 2 factors being multiplied together. So the answer to that multiplication problem would be the product. And since that's in parentheses, we have to do that first before we raise to this exponent. So a way to simplify it, it's kind of like distributive property, where this exponent applies to every single factor on the inside of the parentheses. So it becomes 6 to the fourth, x to the fourth. And if you just kind of look at that and think about how commutative property would work, that absolutely makes sense. All right, calculate the following products without using a calculator. So remember, this is scientific. Well, they're supposed to be scientific notation. This one is, and this one is, but that's technically not, and that's technically not. So I guess this isn't supposed to be converting from scientific notation to standard form. It's just a decimal number times the power of 10, and you always move the decimal point the number of places to the right that the power that the exponent tells you. So since this is literally 100 with 2 zeros, you move it 1, 2 places to the right. This is 7, that's 10 million. And then you'd have to move this 7 times to the right. So 1, 2, 3, 4, 5, 6, 7 means this number times 10 million is blah, 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 is 6,893,000. Okay, 4 places to the right, 1, 2, 3, 4, and 3 places to the right, 1, 2, 3, gives you 92. All right, and moving back toward chapter 6, graph the following points on a coordinate grid. So there's 1, 1, there is 4, 1, and there is 3, 4. Connect the points and translate the points 3 units to the right, 1, 2, 3, and 3 units up, 1, 2, 3. So there you go. This spot corresponds to that spot. And the same with this guy, 3 to the right, 3 up, 3 to the right, 3 up, and then those are the new coordinates. Oh, these frequency relative tables. Let's see what this says. Scientists consider the average growth of kelp to be an indicator of health of marine plants. They also consider the average weight of crabs that live in the kelp beds to be an indicator of the health of the marine animals. But they want to know if there's an association between the health of the sea plants and the health of the sea animals. So marine biologists biologists collected data from different parts of the world and created the following relative frequency table. They considered the average growth rate of the kelp as the independent variable. Okay, so when the kelp is doing well and it's greater than 5 centimeters per day, what happens with the sea life? No, this is less. The average rate is less than 5 centimeters per day. What do we notice about the average weight of the sea life? And when the kelp is greater than or equal to 5 centimeters per day, what do we notice about the growth of the sea crabs? Well, I think this is pretty clear. Most of the sea crabs are 25 or 1/4 of a kilogram or less when the sea kelp is not as healthy. And it looks like that 84% of the sea crabs are between 1/4 and 3/4 of a kilogram in weight when the sea kelp is healthier and growing at a healthier rate. So there absolutely appears to be a correlation there. There's an association between the two. If the kelp rate is low, there is a higher percent of smaller crabs. When the kelp rate is higher, there is a higher percent of larger crabs. All right, enrollment in math courses at Kennedy High School in Bloomington, Minnesota is shown in the pie chart. If there are 1,000 students enrolled in math courses, approximately how many students are enrolled in algebra, geometry, and calculus? Okay, so why do we have, what's going on here? I think that what I was saying here is this combined should be about 25% right there. So this looks like it's about 25%. And if you break this up, if that's 1/2, and that looks like it's like 1/5 of a quarter, that would be like 5%. So I am just absolutely guessing at these numbers, okay? There is no reason why anyone would think that this is exactly 45% and that's exactly 5%. Although I think there's an argument to be made that this looks like it's a right angle there, although we're looking at it from a slanted perspective kind of a view. But I think that's supposed to be about 25%. So based on that, the geometry would be 25% of 1,000. And calculus looks like it's about 1/5 that, so that would be about 50. And this portion, if that's 5%, this has to be 45 because the whole total would be 50%. So I'm guesstimating this part to be about 45%. So whatever this is, multiply it times 9, right? Because 5 times 9 is 45, so 50 times 9 is 450. All estimates, by the way. If you have something close to that, you're in the right ballpark. That's all we need. All right, compound interest. Let's work on this problem. And I'm going to use this calculator because I don't have my Google scientific calculator up. This will work just fine. We worked with this before. We can work with it again. It says, stop it. Well, I'll just keep it like this. Determine the compound interest earned on $220 invested. Okay, so that is the principal at 3.25%. 3.25 is going to be converted to a decimal number, and it is compounded annually for 6 years, which means it's going to get once per year for 6 years. So it means the time is 6. So for this formula, we're going to take 220 plus 1 point. What is the decimal equivalent of 3.25%? 3.25 divided by 100 changes it from a percent to a decimal, so 0.0325. So we're going to add that to the 1 to make it 1.0325. And then we're going to raise that to the power of 6. So what we need to do first, since I'm using this calculator, and this calculator forces me, plus 1, to take what's inside the parentheses and raise it to the power first. And that gives me a multiplier that I'm going to multiply times 220, so I'll do that now. And that gives me $226.54, 226.54. So if they want to know what the new amount is, this is going to be the new amount. But they said determine the compound interest earned. So how much interest was earned? Well, this was your money. So anything over that is going to be the interest earned. So we're going to take 266.54 and subtract away 220, and you get $46.54 was earned over the 6-year period. And that is it for our homework. Hooray. Oh, no, don't do that. So let's move on to whatever we got next. Bye.
Hey, feeling good, like I